First of all, I welcome you all in this lecture, which contains the topic Monotone Convergence Theorem, Fatou's Lemma, and Dominated Convergence Theorem. So, before starting all these things, first we have to know what is the expected value of a random variable, and for which I discuss some useful definitions related to that. Let omega AP is triplet be a probability space. All the random variables are assumed to be defined on this given probability space. Omega represents sample space, A represents sigma field, P represents the probability measure. In mathematics, most of the people call omega as space and represented by capital X, A sigma algebra, and instead of P, they take mu as a measure. So since we are talking about expected values and we are discussing only the probability measure, so our space is omega AP triplet. So first we just recall the definition of expectation of non-negative simple random variables. So what are simple random variables? See, if we represent a function from omega to r, function x from omega to r such that x omega is summation I from 1 to n xi iai omega, where this xi's are non-negative, iai's are indicator functions. That means iai omega is 1 if omega belongs to ai and it is 0 otherwise. So you can see this is a linear combination of these kind of elements. So they take finite values x1 x2 xn on sets a1 a2 an, and these sets a1 a2 an are actually the measurable partition of this omega. So they must be measurable partition of omega. So if I define x in this fashion, then this is known as non-negative simple random variable. The expected value of x is defined as, and it is denoted by ex, which is nothing but xi and probability of ai. This is the expected value of x. Then we define what is the expectation of a non-negative random variable. That means it is not simple random variable. It is non-negative random variable. So as we know that non-negative random variable, if there is a non-negative random variable x, then there exists a sequence xn of non-decreasing, which is a non-decreasing sequence of non-negative simple random variables converging to x. And then we can define expected value of x, which is nothing but the limit of n goes to infinity of expected value of xn. Xn's are non-negative simple random variables and their expectations are well defined in above definition. So we can find out the limit of this. How we can find out the limit and why? Because this xn is a non-decreasing sequence. So expected xn by properties of expectation, this will be non-decreasing sequence. So it will be non-decreasing sequence. So whether it will converge to a positive, it will converge to a finite number or it will diverge to plus infinity. So there is no problem in taking the limit. And now we define expected value of an arbitrary random variable. So if there is an arbitrary random variable x, we can separate their positive part and negative part. Now what is the positive part? We define positive part x plus, which is equals to x if x is greater than or equal to 0, and it is 0 if x is negative. And negative part of x is represented by x minus, which is equals to minus of x if x is negative and 0 otherwise. So both the x plus and x minus, they are actually positive and negative parts, and we define expected value of x is expected value of x plus minus expected value of x minus. But we know that expected value of x plus may be plus infinity, expected value of minus x may be expected value of x minus may be plus infinity. So if both are plus infinity, this will be infinity minus infinity kind of thing. So we write a condition that provided at least one of the term right hand side of above equation is finite. So in this way we define the expected value of x. I am not giving details of these things because I assume that you know all these things. So I am just recalling the definitions. And now this expected x of random variable x is also called the integral of x over omega with respect to the probability measure p and is also denoted by integral x dp or simply integral x dp or in very simple manner integral of x. So expected value of x is actually the integral with respect to probability measure p. And now there is an integrable random variable. We know that expected value of x may be plus infinity or that kind of thing. So or minus infinity also. So a random variable x is said to be integrable over a set A if expected value of x indicator A exists and is finite. That is important, that integrability is actually related with finiteness of the expectation. We simply say that x is integrable if expected x exists and is finite. These two things are there. So if expectation is finite, we call it integrable random variables. So why these theorems are there? Monotone convergence theorem, Fatou's lemma, and dominated convergence theorem, because there was a question. And what was the question? Question was this: if xn is a sequence of random variables converging to the random variable x, that is, if xn omega converges to x omega for each omega in capital Omega, that means pointwise convergence. The question arises, does it follow that the expected value of xn also converges to expected x? That is our question. It means if xn converges to x, then expected value of xn converges to expected value of x or not. So in this equation, this is the expected xn and this is the limit of expected xn. We want to know whether we can interchange these limit and expectation. That means can we write it down expected value of limit xn in this way. So this is our question, whether we can do this or not. In general, the answer is no. So first we will see a counterexample which shows that the answer is no, and then we will find out conditions under which this equation holds. That means the monotone convergence theorem and dominated convergence theorem provides the conditions under which this equation holds, and both of the theorems were given by Henry Lebesgue. So they are also known as Lebesgue monotone convergence theorem or Lebesgue dominated convergence theorem. First we discuss an example. In this example we take omega as a unit interval 0, 1, and the sigma field is the Borel sigma field defined on unit interval 0, 1, and probability measure we are taking uniform Lebesgue measure. Then we define xn omega, which is nothing but 2 to the power n indicator function of 0 to 2 to the power minus n omega. That means it takes value 2 to the power n if omega is lying between 0 to 0 to 1 by 2 to the power n, and it takes value 0 if omega is bigger than 1 upon 2 to the power n. So you can see here, if omega is bigger than 1 upon 2 to the power n, so we can write it down 2 to the power n greater than 1 by omega, or if I take log, then n is greater than log of 2 1 by omega, then xn omega is 0. So for each omega, xn omega is 0 for all n which are bigger than log base 2 1 by omega. So that means when n is very large, omega is fixed, then it will always cross this number, because there are natural numbers which can cross any real number. So for large n, xn omega will become 0. So xn omega will converge to 0 as n goes to infinity. So now we have xn omega which is converging to 0. If I define x omega to be 0, identically 0, so we are saying that xn omega converges to x omega, and where x omega is identically 0. No, but expected value of xn, so expected value of xn by definition it will be 2 to the power n and measure of this set. So that lambda, that means Lebesgue measure of this set, and we know that Lebesgue measure is of AB is B minus A, so it will be 2 to the power minus n, and 2 to the power n multiplied by 2 to the power minus n will give you 1. And this expected value of xn is 1 for every n. That means it is a constant sequence, so it will converge to 1. That means limit of xn will be 1. But you know that xn omega converges to 0. That means expected value of limit xn is expected value of 0, which comes out to be 0. And we can easily see that limit of expected xn is 1. but expected value of limit xn is 0 and both are not same. So this is an example where we can see that we cannot interchange this limit and expectation easily. So now our target is to find out the conditions under which we can do this, and fortunately Libre has given us conditions, and first theorem is monotone convergence theorem. So it says that let xn be non-decreasing, that means the first condition is the sequence must be non-decreasing sequence of non-negative random variables converging to random variable x. Then limit n tends to infinity, expected xn is nothing but expected x. That means we can write it down. Limit n tends to infinity, expected x is equals to expected value of limit n tends to infinity xn. That means we can interchange the limit and expectation. So there are two conditions, that the sequence must be non-decreasing, and another condition is sequence must be non-negative. So in short, we will write this way, that xn is a non-negative, non-decreasing sequence and it is converging up to x. So if xn's are non-negative, expected value of xn will be non-negative. If xn's are increasing, increasing means non-decreasing, then expected xn is increasing up to this. So in short, we will write this way. So we will see the proof of monotone convergence theorem. So with every random variable xk of the given sequence, since xk is non-negative random variable, we can associate a non-decreasing sequence xkn of non-negative simple random variables converging to x. This is a property that you can always associate a non-decreasing sequence of non-negative simple random variable converging to a non-negative random variable. So since xk is non-negative random variable, I can find out xkn such that x11, x12, x13, x1n, this sequence is converging to x1, then x21, x22, x23, x2n it's converging to x2, then this x31, x32, x33, this sequence converging to x3, and so on, xk1, xk2, xk3 is converging to xk. Now see one thing very carefully, that this sequence, if you move from left to right, this is an increasing sequence converging to x1. I will call non-decreasing as increasing for the simplicity. So if you move from left to right, it is increasing. In second line, if you move from left to right, it is increasing, and so on. But you know that x1, x2, xk, that means sequence xn, that was also non-decreasing. So that means this also, if you move from up to down, it is increasing. So from left to right increasing, from above to down it is increasing. Now let yn is maximum of xkn, where kn belongs to 1 to n. That means it is a maximum of x1n, x2n xnn. So since x1n, x2n, xnn, all of them are non-negative simple random variables, we know that their maximum is also non-negative simple random variable. So yn is non-negative simple random variable. Yn is the maximum of the nth column, maximum of the elements of nth column of the following matrix. If you see it carefully, what is y1? y1, that means n is 1. So k can take only one value, which is 1. So maximum of x11. So this is x11. So this is y1 actually. Then y2 will be maximum of these two, x12 and x22. y1, y3 will be maximum of these three, and so on. yn will be the maximum of these three. So maximum y1 is nothing but x11, y2 is maximum of these two elements, y3 is maximum of these three elements, and so on. Yn is maximum of these n elements. Now we will see that this sequence yi is also non-decreasing. So if you see it carefully here, now this was there. If you move from left to right, it is increasing. So if I find out y2, for example, y2 is maximum of these two. But you know that x12 is bigger than x11. So maximum of these two will be bigger than x11. That means y2 will be bigger than y1. Then maximum of these three will be bigger than maximum of these two, because you are moving from left to right. So maximum of these three will be bigger than maximum of these two. That means y3 is bigger than y2, and so on. Y1 is smaller than y2, y2 is smaller than y3, and so on. So this yi's are actually non-decreasing, non-negative, simple random variables. We will show that this will also converge to x. We will prove it. So clearly yn is non-decreasing sequence of non-negative simple random variables with this condition. How these conditions? See, it is very easy to see. Yn was maximum of, see, yn is maximum of these. So if it is maximum of these, then it will be bigger than in any one of them. And yn is maximum of these three, and you know that you are moving towards this, and this is xn. Xn is bigger than all these, because x1 is bigger than this, x2 is bigger than x2n, x3 is bigger than x3n, xn is bigger than xnn, and x1 is bigger than x1, x2, all of them. So xn is bigger than maximum of this. So we are getting yn in between these two numbers. And since yn is in between these two numbers, their expectation will also follow the same inequality. So with these two inequalities, we will do something. So I write down these two inequalities once again. Now see, xkn is non-negative simple random variable sequence. This was converging to xk. Yn is non-negative simple random variables. Xn is also sequence. So if I take limit n tends to infinity. So if you consider that limit n tends to infinity in these two inequalities, and using the definition of expectation of non-negative random variable xk. See, xk was non-negative random variable. Xkn was a sequence converging to xk. So we know that expected xk is nothing but expected value of limit of expected xkn. So this expected xkn, first this will converge to xk. Yn we do not know where it will converge, so I just write it down, limit n tends to infinity yn, but we are sure that yn will converge because yns were non-negative simple random variables which were non-decreasing also, and xn converges to x, we know. So if you apply n tends to infinity in this inequality, this becomes xk, this becomes limit n tends to infinity yk, and this becomes x. Now this expected xkn, you know that if you put limit here, and since these xkns are non-negative, non-decreasing simple random variables and they are converging to xk, then their limit of expected xkn will converge to expected xk. Again, expected yn, it will converge, we do not know, but I can take the limit because this will also be non-decreasing sequence. Expected xn, we can take the limit, we do not know where it will converge, but we can take the limit. Then we know that yns were non-decreasing, non-negative, simple random variables. And for simple random variables, we know that by definition, I can take limit inside. Next step is we are taking this limit inside. This is the by definition. Now further, we take limit k tends to infinity. Now we are taking k tends to infinity. Now you know that xk is a sequence which converges to x. This x is as it is. There is no k, so it will be remain as it is. This expected xk, we do not know where it will converge, but I can write it down, limit k tends to infinity xk, and there is no k, so it will be as it is, and this is this. Now you see carefully what we are writing, x is less than or equal to limit yn, which is less than or equal to x. That means limit yn is nothing but capital X. This was our claim. Similarly, this is limit n tends to infinity expected xn, right hand side, and left hand side is limit k tends to infinity expected xk. Both are same. You just change this k to n. So again this in between term will be same as this. So we have two things. First is limit yn is nothing but x, and second is expected value of limit yn. Expected value of limit yn is nothing but limit n tends to infinity expected xn. But you know that expected value of limit yn is x. So this will be expected x. So if you see the last line, limit of n tends to infinity expected xn is nothing but expected x. That means we can interchange the expectation and limit. So this was the proof of monotone convergence theorem. I just repeat once again the key points of the proof. And what are those key points? First, we construct a sequence of non-negative random variables, non-decreasing sequence, which will converge to x1 and x2 and x3 and so on. And out of these sequence, we find y1, y2, yn such that y1 is maximum of this, y2 is maximum of these two, and so on. So this y1, y2, yn, this sequence will also be sequence of non-negative simple random variables. We first show that this sequence is non-decreasing and it is in between these two numbers. Then we write down the same inequality with expectation, and with the help of these two inequalities, first we take n tends to infinity, and you know that xkn converges to xk, xn converges to x, and this I can write down just in the terms of limit. Expected xkn converges to expected xk, this in terms of limit, expected xn in terms of limit. Then we, since yns are a non-decreasing sequence of non-negative simple random variables, I can take this limit inside by definition, and then we choose that k tends to infinity, then xk tends to x. This is as it is, then this will become. So now you can say that this limit yn is bigger than x and smaller than x. That means this is equal to x, and similarly this left hand side and right hand side are both are same. So this expectation and this limit, both limits will be same, and this is nothing but expected x. So this was the. Now there are some corollaries, and first corollary is this: if xn is not bounded below by 0, then what will happen? So this corollary says if xn is bounded below by any random variable y which is integrable. So expected modulus of y is finite, means it is integrable. So if xn is bounded below by any integrable function and it will increase to x, then expected xn will also be bounded below by expected yn and it will increase to expected x. A proof is very simple, so I have skipped the proof. You can just do the proof. You just define a new sequence Zn which is xn minus y and apply monotone convergence theorem on Zn. You will get the result. Now what happens if instead of non-decreasing we take non-increasing, and instead of non-negative we take non-positive? Then this corollary says the limit, the same result will hold for the non-increasing non-positive sequence of random variables. And proof is again very easy. You just take new sequence Zn which is minus of xn. So if you take minus of xn, this new sequence will become non-decreasing and non-negative. So you can apply again monotone convergence theorem and you will get the answer. The question is this: what happens if this we know that okay, non-negative and non-decreasing it is okay, non-increasing and non-positive it is okay. Then what about if it is non-increasing and non-negative? So you can find out counterexamples such that if you take non-increasing and non-negative, that means non-negative and decreasing sequence, then this result will not hold. You can find examples. So I have not included any example of that kind, but you can easily find that example. So one more application of monotone convergence theorem, which is very simple and which is very useful, that if xn be a sequence of non-negative random variables, then expected value of sum from n from 1 to infinity xn is equals to summation n from 1 to infinity expected xn. That means you can interchange this sum and expectation easily. And what is the condition? Condition is only the sequence should be non-negative. So this is proof is based on monotone convergence theorem. And how we prove it? We just define a sequence Zn which is xk, k from 1 to n. You can easily see, since xk's are non-negative, this Zn, if you take Zn plus 1, it will be k from n plus 1 to xk. That means it will have one extra element xk plus 1, which is non-negative. So Zn will be smaller than Zn plus 1 and so on. So that means Zn is increasing sequence. Okay. And since xk's are non-negative, Zn's will be non-negative. So Zn's are non-negative and increasing, and it will increase, of course, it will increase up to n from 1 to infinity xn. Okay. Then if Zn will have this property, then expected Zn, which is nothing but, since it is finite number of elements, expected Zn, I can write it down, k from 1 to n expected xk. So this will converge to this n from 1 to infinity expected xn. But what you are saying? You are saying that Zn converges to this element, this random variable, and expected Zn converges to this. By monotone convergence theorem, we know that if Zn converges to, for example, Z, then expected Zn converges to expected Z. So that means this is expected Z, nothing else. So this is this quantity which is written here. This is expected Z, that means it is this one. So this was the proof using monotone convergence theorem. And then since we know that monotone convergence theorem requires non-negative and non-decreasing sequence. If you convert non-negative to non-positive, then you have to convert non-decreasing to non-increasing. But if you want only non-negative, not increasing, not decreasing, then what would happen? Then there is a Fatou's lemma which says that for a sequence of xn of non-negative random variables, expected value of limit inferior xn is less than or equal to limit inferior expected xn. That means with the limit inferior, if you interchange the expectation, that there will be no inequality, there will be not equality, there will be inequality of such kind. This is also useful result, Fatou's lemma. So we will see the proof. Proof is not very tough. Proof is actually again based on monotone convergence theorem. So for this we define yn, which is infimum of xk, k is greater than or equal to n. That means it is infimum of xn, xn plus 1, xn plus 2, and so on. So you know that from real analysis, this infimum xk, k from n to k greater than or equal to n, this is an increasing sequence, and this will converge to limit inferior of xn. This is from real analysis. If you fix omega, then you know that this yn will converge to limit inferior xn. And since xn's are non-negative, so yn will be non-negative because this is inferior of xk's. So yns are non-negative, they will increase to limit inferior. Then by monotone convergence theorem, expected value of yn will increase expected value of limit inferior xn. That is for sure. But focus on yn. Yn is infimum of all these. All these means xn, xn plus 1, xn plus 2, and so on. So if yn is infimum of these, yn will be smaller than every one of them. That means I can write it down, yn is smaller than xn. That means one of the element for every n. So since yn is smaller than xn, their expectation of yn is also smaller than expectation of xn. Now see it carefully. This expectation of yn, this is a sequence of real numbers. Expectation of xn, this is again a sequence of real numbers. So if I call it an and bn, then you know that an is less than or equal to bn. Then this limit an, it is a converging sequence. It converges to expectation of limit inferior. But you do not know anything about expected value of xn. So there are two sequences, an and bn. An is less than or equal to bn. An converges to a. Then we know that a will always be smaller than limit inferior of bn. So that we are going to write it down, that expected value of yn, if I find out limit of this, then this will always be smaller than limit inferior of this. But limit of expected yn is nothing but expected value of limit xn. So we have shown that limit expected value of limit inferior xn is smaller than limit inferior expected xn. This was Fatou's lemma. We will see some corollaries of this. So here again xn was non-negative. So if instead of non-negative we bound it by y, and where y is an integrable function, then same limit holds, same equation holds. Then if xn is bounded above by z, then this expectation limit inferior xn will converge, will be expected value of limit superior xn is greater than or equal to limit superior expected xn. And if xn is bounded below and above by y and z are integrable functions, and xn converges to x almost surely. So convergence almost surely, I hope you know that xn converges to x almost surely means if we find out those omega for which xn omega converges to x omega, then probability of that set which contains those omega which will be 1. So that means xn converges to x with probability 1. That is almost sure convergence. So if these two things are there, then again limit n tends to infinity, expected xn will be expected x. That means you can again interchange the limit and expectation if these conditions holds. Okay. So proof, we will see the proof. First we will define, for this we will define xn minus y. For this we will define z minus xn and so on. Xn minus y. Now you know that this xn minus y will be non-negative. So you can apply Fatou's lemma on un, and you will get expected value of limit inferior un is less than or equal to limit inferior expected un. But what is limit inferior un? Un is xn minus y. So I will write it down, limit inferior of xn minus y, because y is a constant, so there is no point to write down limit inferior with y. And limit inferior expected un, so you know that expected value of un is nothing but expected xn minus expected y, so I have written that. Now we know that expected value of limit inferior n minus y, we can separate them. So expected value of limit inferior xn minus expected y, it is less than or equal to limit inferior of expectation xn then minus of expectation y, because it is again a constant, so there is no meaning of limit inferior on that, or you can say limit inferior comes out to be expected value of y. Now since you know that y was integrable, so y is integrable means expected y is finite. So if expected y is finite, we can add this expected y on both the sides and we will get this expected value of limit inferior xn less than or equal to limit inferior expected xn, and this completes the proof of part 1. Now we define Vn, which is z minus xn. So again this will be non-negative random variables, sequence of non-negative random variables. Again we apply Fatou's lemma on Vn. Then expected value of limit inferior Vn is less than or equal to limit inferior expected Vn. Now limit inferior Vn, you can write it as z minus xn. Expected Vn, which is z minus expected xn. Then limit inferior z means z. Limit inferior of minus expected minus xn. You know that from real analysis that limit inferior of minus an is minus of limit superior an. So it will become limit minus of limit superior xn. Similarly, this is expected z and expected xn separate. Then this expected value of z minus expected value of this, again we will apply the same thing, limit inferior of minus of expected xn will be minus of limit superior of expected xn. Then the same thing, since z was integrable, expected z will be finite, so we can subtract expected z on both the sides and we will have this. Now since there is a minus sign on both the sides, if we multiply this inequality with minus, then we know that this inequality will be changed and we will have this, and which completes the proof of part 2. Now for part 3, you have to use something from this. Xn converges to x almost surely. That means limit inferior xn and limit superior xn and x, all these three are same almost surely. Because for convergence, limit inferior, limit superior and x must be same. So we start with expected x. It is nothing but, since you know that if two random variables are equal almost surely, then their expectation will also be same. So since x is equal to limit inferior xn almost surely, expected x will be expected of limit inferior xn. Now you know that from part 1 that expected value of limit inferior xn is less than or equal to limit inferior expected xn. Then you know that limit inferior of real number will be less than or equal to limit superior of those numbers. Now you use part 2, which says that expected value of limit superior is bigger than limit superior expected xn. Then you know that this expected value of limit superior is expected x. So what we are getting, we have started with expected x and end with expected x. So that means in between all items in between will be same. So we are getting this, that expected value of limit inferior expected xn, this limit inferior expected xn, this limit superior expected xn, and this expected x. All these three are same. That means what you are getting, limit inferior of a sequence, limit superior of that sequence, and this number. All these three are same. That means limit exists, and limit of expected xn is nothing but x. So this was the part 3 of Fatou's lemma. Now with this part 3, you just I just recall part 3. So this is the part 3. So if I replace this y and z with same element, I want to replace that. So I am writing this mod xn less than or equal to y. So mod xn less than or equal to y is integrable. Then this holds, and this again follow from the part 3, because mod xn less than y means minus y less than xn less than y. So if y is integrable, minus y will be integrable. So using part 3, we have this result. Now question is important, as we know that almost sure convergence is stronger than convergence in probability. So next question arises, can we weaken this condition? That means, can we replace this almost sure convergence into convergence in probability? Answer is yes, and that is dominated convergence theorem. It says that if mod xn is less than or equal to y almost surely, where y is integrable, then this xn converges to x in probability is sufficient to imply expected xn converges to expected x. That means you can replace that almost sure convergence with weaker condition, which is convergence in probability. This is the dominated convergence theorem. In this lecture, I am not going to prove this. So what we have discussed in this lecture, first we recall the definitions of expected value of non-negative simple random variables, then non-negative random variable, then arbitrary random variable. Then we have defined what is integrable function. Then we have provided one example which shows that that expected value of limit of expected xn may not be equal to expected value of limit xn. And then we have shown conditions under which this can be done, which is monotone convergence theorem, then some corollaries of MCT, and one of the important corollary was Fatou's lemma. And then we have using Fatou's lemma, we have again found some corollaries, and then we have given the statement of the dominated convergence theorem. and I think I'll try to probe this in our next lecture. Hope this lecture will be useful for you. I would like to have your comments so that in future I can improve.